and welcome back, Mindsetters. Hope you had a nice little break. You went and did whatever you had to do. You went to the bathroom, you spoke to mom, you spoke to your dad, you were cooking dinner, you cut onions, whatever you had to do now needs to stop so you can pay attention. Tell them, wait, I need to pay attention right now. Phil's on TV and Ty, so we need to pay attention. But on that note, Mindsetters, make sure that you post. Let us know what you guys are thinking. And before I forget, I want to send a quick shout out to Liberty. Thank you for sponsoring the show. And on that note, I just want to remind you, Mindsetters, that guys, if you're looking for these questions, it's simple. It's written. It's in the images folder in the albums for Learn Extra. It's under Grade 12 Physics Revision. Make sure you go there and you can follow along with us. I've posted up all the questions in order for you, so it's nice and easy. You guys can download them onto your phones, onto your laptop, whatever you're using. But on that note, this is where I hand over to Phil, who's going to continue the lesson. Take it away, Phil.
Thanks so much, Ty. Okay, well, as Ty said, sometimes the writing is a little bit small. We recommend that you actually download these and follow through with us. Okay, I'm going to be reading through the questions, but sometimes a little bit, we've had to cram a whole bunch of exam questions onto one board. So please bear with us. The writing is tiny, but there's a lot of good info there. And as we said, get on the Facebook page. They're all there. Okay, so now 2.5 is where we left off. The diagram below represents two pulses. So let's take into account the things which we are talking about. So two pulses, each of amplitude A. Now that's pretty important. So that means that they are the same size. They're traveling in opposite directions along a slinky coil. Doesn't matter what they're traveling on, but basically they're coming towards each other. Now I want you to see this. These waves have got exactly the same amplitude. One is above, one is below. So if I was to label them as parts of a wave, that one would be a crest, and this one would be a trough. So the crest has got positive amplitude A. So if that's got positive A and it meets a trough, oh, wait a minute, take a look at that. A trough has got a negative amplitude of A. If you add these together, we're going to get something which is going to be 0. That's what I'm expecting. When these two come together, positive A, negative A should cancel out. We should have absolutely nothing. So remember what I said. Predict your answer first and then go looking for it. Not the other way around. Because you're going to get everything here looks right. The examiners have made sure that everything looks kind of okay. So what we're going to do is we're going to look for the option which is what we think it is. And the only option which leaves us with that is option B. So like I said, there we go. We think it's B, but what we're going to do is take all the others off the table. Well, is A correct? Well, would they add up to make double A? No. They were going in opposite directions. That would be correct for constructive crest-crest. One crest on top of the other crest, that would be constructive. We're looking for destructive. Same thing in C. If I look at option C, I see a double trough. I see two troughs underneath each other. That's also not correct. What about option D? Well, option D doesn't look right. What we've got is a Slinky's coil, which is actually splitting in two, which is absolutely not right. That is impossible. So our correct option for 2.5, if you're doing this with us, is option B. Okay, well, we're going to continue through these multiple choice. Let's carry on with 2.6. Okay, so now it says a set of identical light bulbs. Let's highlight that important piece of information. There we go. We've got identical light bulbs are connected as shown in the circuit diagrams. The internal resistance of the battery is negligible. That means that we can ignore it completely. Okay, which one of these circuits will the light bulbs glow the brightest? Well, here, I can't predict what they're going to show me, so I've actually got to consider each option. Now, what you've got to do is you've got to play this smart, because 3 of these have got something in common, and there's one which stands out. Now, all of them have got 3 cells, so they've all got exactly the same amount of EMF. So I know that there is the same amount of power going into these circuits. All right, so that can't be it. Now what I've got to do is I've got to realize what is different from one to the next. I can see that they are connected either in series or in parallel. Well, I've got to remember the following, is that if you connect light bulbs in series, you divide up the voltage. If you connect them in parallel, they receive exactly the same voltage. Well, that makes my choice quite easy, because option A is the only one which doesn't divide up the voltage. Each one of these light bulbs would get exactly the same and full voltage. Okay, so now we're not entirely sure about this, so we think it's option A, but let's just make sure. Let's go around the other options. We're not entirely sure at this stage. Option B, what's going to happen is you're going to divide up your voltage among 4 because they're connected in series. B is actually going to be the dimmest. Okay, well now between option C and D, what you're actually going to find is that they're actually connected in exactly the same way, except we've got a Wheatstone bridge in the case of D, and over on option C, it's just unconnected in the middle. But what you'll find is that C and D actually have the same brightness. Because what's going to happen is I've got these 2 light bulbs in series with these 2 light bulbs sharing out the voltage. That's not what you want. If you want a bright light bulb, you want as much voltage as possible. Again, in option C, we've got the series combination. That confirms that option A is the only one that it can be. And the reason for that is because we've got that lovely parallel situation happening there. Okay, so moving onwards. All right, here we go. A little bit of a definition one. 2.7. So if you're following with us, I'm hoping that you're checking answers, seeing how you're going. The unit of measurement of, okay, now let's just make sure that we're talking about the same thing. The rate of flow of charge, okay? The rate of flow of charge. Okay, well, I'm not entirely sure about this. The rate of flow of charge. Well, let's make a formula out of it. If we don't know about it, let's try and predict what it is. Rate of flow. If I'm looking for rate, I'm going to divide it by delta T. Okay? Flow of charge. Charge is represented by Q. Oh, wait a minute. If I go look at my formula sheet, I can actually recognize what's going on here. That's the way that I can calculate I. And I stands for current. So let's go see if we can't find current, and let's see if we can't find something which works with current. Okay, so the rate of flow of charge, well, that's current. A watt is a measure of power, so it can't be option A. A volt is a measure of, and careful about this, volts and current are very, very different. Volts and amperes are measures of very, very different things. They both have to do with the movement of charge. Volt is how much energy you give those coulombs of charge. So that is not it. Wait a minute, I think I've got a winner here. What we've got is an ampere, and an ampere is a measure, there we go, of current. So we think we're right. Now let's just go to option D. Option D says coulomb, okay? And coulomb is a measure of the amount of charge, not the rate of flow of charge. See what they've done there. They've purposefully put in something just to trip you guys up. It sounds kind of right. Coulomb is something to do with charge, and if you didn't learn properly, you would have taken that one. So option C is the correct one for question 2.7. Okay, now 2.8 I particularly like because this is a trick question. Okay, now it says point P. Let's identify point P. Point P is over here. It is a distance x. There we go. Distance x is drawn in for us. Okay, from the positive plate of a parallel plate capacitor. Whoa, there's a thing which I really like. Parallel plate capacitor shown in the diagram below. Well, if I remember correctly, a parallel plate capacitor has got something quite special about what goes on in between those 2 plates. But let's not get too far ahead of ourselves. Let's read the question first. The magnitude of the electric field. Oh, wait a minute. I know something about the electric field between parallel plates. Is E. So it's got a value of E. Now, at a distance of half x. So in other words, if I placed point P much closer, in other words, x over 2, so half of x, from the positive plate, the magnitude of the electric field will be, okay, well now everyone's going crazy here. They're going, oh goodness, all this maths and all these ratios. They've tricked you. What we didn't realize and what we didn't learn from grade 11 is that parallel plates have actually got an even field. It doesn't matter where you put P in between these, the field remains consistent all the way through. And they've put in all these scary fractions just to scare you. So I can jump straight to my correct answer, and that is C. All of these other ones talk about a different electric field strength, and that is entirely unnecessary. It stays exactly the same. They've started putting in all these numbers there just to confuse those of you that didn't listen carefully. parallel plates have got a consistent and even electric field all the way through. Doesn't matter where you are. If you're at X, 2X, half X, doesn't matter. The field strength will be exactly the same as it was before. Okay, we're doing pretty well. We're almost all the way through these two. Let's start taking a look at some of our wave stuff. Now, this stuff I particularly like. It's really, really interesting. It's physics which is relatively new. It's not 300 years old, invented by some dude with gray hair and long beard. Okay, this is really interesting stuff. Okay, so which one of the following descriptions best explains the formation of a line emission? Okay, so let's just make sure that we know what we're talking about. A line emission spectrum. Okay, well, I've got to make sure that I know what I'm talking about when I say a line emission. Emission is a process of giving off a photon when an electron relaxes. So if I've got a nucleus over there, and I've got an electron which is orbiting, and it's got several orbits around it, what happens is an excited electron over there is going to drop down to a lower energy level, and that will give off a photon of light. So I've got to make sure that I understand what's going on. This is the process of emission. Let me just repeat what I said. Okay, an electron, which is an excited or upper state or heightened state of energy, loses its energy by dropping down to a ground state. What happens is that extra energy gets given off as light of a particular frequency, and that's where the spectrum comes from. Okay, so now we've decided on our answer. Let's go look for it. Well, they say A, white light passes through a cold gas. Now that sounds kind of right, because that does make one of my spectra, but that makes an absorption spectrum. So they've tried to trick me there, because it sounds right, and it does make a spectrum, but it's not the one that I'm looking for. Okay, white light passes through a triangular prism? Definitely not. That's the one which gives me my full spectrum. Again, I've got to be so careful. All right, then they start talking about electrons. I'm interested. Let's read further. Electrons in the ground state move to a high energy level. That doesn't sound all that correct. Now, one thing which really bothers me about this is it's asking electrons to go up. That is a sign of absorption. So that can't be right, because we're looking for emission. Absorption is when the electrons in the ground state go up to a high energy level. So that's wrong. So I'm left with only option D. Well, let's see if it's right. Electrons in the excited state, aha, that's what I'm looking for. Excited state, there we go, move to a lower energy level. That is when emission takes place. So option D is the winner. So question 2.9, option D is definitely the correct one. Okay, I hope you guys have been following very, very nicely. We're on our last multiple choice question, and then we're going to take a short break before we come to some of the long questions. So just the last one quickly. Which one of the following electromagnetic waves has the shortest? Guys, you got to know your EM spectrum, hey? You got to make sure that you know which order these guys are in. Well, let's just do a quick revision session on which way they are. So what I'm going to be doing is I'm going to be going from long to short. And I recommend that you actually do this in your exam, and you actually find a way to remember the order of these. So from long, I'll start out from radio, and then I find my friends microwaves, ready for some popcorn. So microwaves, then I start with infrared, then visible, okay, and then UV, then X-rays, and then all the way on this side, I find gamma rays. Okay, so now I've already picked my answer, and I hope that you actually know the order of these. So from longest, it starts from radio, goes through microwaves, infrared, visible, UV, X-rays, and then gamma rays. Okay, well, let's try and find out which one we're talking about. So the shortest wavelength over here, I'm looking for an option which says to me gamma rays. And there we are. Gamma rays is right there in front of me. Option B is correct. Radio waves are the longest. Infrared rays, well, those are even longer than visible. Ultraviolet are longer than X-rays and gamma rays. Option B is the correct one. But I think what we're going to do is take a short ad break. What do you think, Ty? How's the page looking?
So too. The page is looking really good. So that's always a good sign. So mindsetters, make sure you get on the page and keep chatting, because I'm loving what's happening and I'm loving the guys who are posting and just answering questions. So everyone's following along. So guys, I'm glad that you're finding this very helpful. But do not disappear. We'll be right back after the short break. See you soon.